Thermonuclear fusion ignition by nuclear fission. At the beginning of the 20th century, understanding the nature of the energy source that powers the sun and other stars was one of the most important problems in physical science. Initially, gravitational potential energy released during protostellar contraction was considered, but calculations showed that the energy released would only be sufficient to power a star for a few million years, and life has existed on Earth for a longer time. The discovery of radioactivity and the developments that followed led to the idea that thermonuclear fusion reactions power the sun and other stars. Thermonuclear fusion reactions are called thermonuclear because temperatures on the order of 1,000,000 degrees Celsius are required. The principal energy released from the detonation of hydrogen bombs comes from thermonuclear fusion reactions. The high temperatures necessary to ignite H-bomb thermonuclear fusion reactions comes from their A-bomb nuclear fission triggers. Each hydrogen bomb is ignited by its own small nuclear fission A-bomb. In 1938, when the idea of thermonuclear fusion reactions as the energy source for stars had been reasonably well developed, 1939, nuclear fission had not yet been discovered. Hahn and Strassmann 1939. Astrophysicists assumed that the 1,000,000-degree temperatures necessary for stellar thermonuclear ignition would be produced by the infall of dust and gas during star formation, and have continued to make that assumption to the present, although clearly there have been signs of potential trouble with the concept. Protostar heating by the infall of dust and gas is offset by radiation from the surface, which is a function of the fourth power of temperature. Generally, in numerical models of protostellar collapse, thermonuclear ignition temperatures, on the order of 1,000,000 degrees Celsius, are not attained by the gravitational infall of matter without assumption of an additional shockwave-induced sudden flare-up. Hiroshi and Nakano 1965. Larson 3 1984, who result optimizing the model parameters, such as opacity and rate of infall. Staller et al. 1994. After demonstrating the feasibility for planetocentric nuclear fission reactors, I suggested that thermonuclear fusion reactions in stars, as in hydrogen bombs, are ignited by self-sustaining, neutron-induced, nuclear fission. Herndon 1994. The idea that stars are ignited by nuclear fission triggers opens the possibility of stellar non-ignition, a concept which may have fundamental implications bearing on the nature of dark matter. Herndon 1994, and dark galaxies. Herndon 2006. I now suggest the possibility that hot Jupiter exoplanets may derive much of their internal heat production from thermonuclear fusion reactions ignited by nuclear fission. Unlike stars, hot Jupiter exoplanets aren't sufficiently massive to confine thermonuclear fusion reactions throughout a major portion of their gas envelopes. One might anticipate instead fusion reactions occurring at the interface of a central, internal substructure, presumably the exoplanetary core, which initially at least was heated to thermonuclear ignition temperatures predominantly by self-sustaining nuclear fission chain reactions. After the onset of fusion at that reactive interface, maintaining requisite thermonuclear interface temperatures might be augmented to some extent by fusion-produced heat, which would as well expand the exoplanetary gas shell, thus decreasing the exoplanet's density. Through good science, resourcefulness, and hard work, exoplanetary astronomers have opened a new window of opportunity to understand the nature of remote planetary systems as well as our own solar system. As scientists attempting to understand those observations and the inferences that might result therefrom, we have the responsibility to be objective, perspicacious, imaginative, and open-minded. This brief communication is presented in that spirit.